ओके, चला आपण जेवढे आहेत तेवढ्यांची ॲक्टिव्हिटी स्टार्ट करूया. अदरवाईज आपल्याला वेळ पुरणार नाही. सो कोण पहिल्यांदा स्टार्ट करताय?
मॅम मी करते.
ओके.
Is my PPT visible or virtual lab visible? Hello.
हां, येस.
Okay. So today, Pallavi and I are going to present a virtual lab in front of you. So the aim of the virtual lab is to understand the working principle of thermocouple. Ritik, can you please unmute your mic? Mute your mic. The objective of the experiment is to understand thermoelectric effect, to study static and dynamic characteristics of thermocouple, and study the effect of thermowell as well as the sheath. So now I request Pallavi to carry on with the theory part. Pallavi, hello.
Hello, am I audible?
Pallavi? Yes.
Okay. So basically, thermocouple is a sensor which is used to measure temperature. It is made up of two wires of different metals joined together at one end to form a junction. And the thermocouple always outputs in a millivolt. The basic, we can say, thermoelectric effect. The thermocouple works on thermoelectric effect. So what is thermoelectric effect? A thermoelectric device creates a voltage when there is a difference in temperature on each side. Or conversely, when a voltage is applied to it, it creates a temperature difference. The working principle of thermocouple are based on following three effects: Seebeck effect, Peltier effect, and Thomson effect. So first one is Seebeck effect. When two wires composed of dissimilar metals are joined at both ends and one of the end is heated, there is a continuous current which flows in the circuit. So voltage is created. Uh, in this figure, there is only one junction, but Seebeck states that there are two wires of dissimilar metals. They are joined at two different ends and one of the end is heated. That heated end is called as hot junction and the second one is called as reference junction or cold junction. Then there is temperature difference between them, and due to this continuous current is flowing through the circuit and voltage is created. Second one is Peltier effect. It is completely reverse phenomenon of Seebeck effect. If the electric current is flowing through the junction connecting two materials, it will emit or absorb heat per unit time at the junction to balance difference in the chemical potential of the two materials. Next one is Thomson effect. The evolution or absorption effect of heat when electric current passes through a circuit composed of a single material with temperature gradient difference along the length. Here, there is only one material is used. It says that there is temperature gradient when we are heated when gradient. In this figure, there is when current is given to cold junction to hot junction or maybe low temperature to high temperature, then here heat is absorbed, and inversely when current is given from high temperature to low temperature, then heat is liberated. Hello, am I audible?
Yes, yes.
Okay. So what is the need for reference junction or cold junction or CJC? Here CJC stands for cold junction compensation. To measure the temperature of one junction, the other junction is kept at some reference temperature as I said, it is also called as cold junction. As this is done by using ice bath, but using ice bath is not convenient for most measurement and control applications. So instead of ice bath, we use thermistor. Thermistor is a resistance thermometer, and thermistors are made up of semiconductors. So next, next one is software compensation. It is the most versatile technique used for measuring thermocouple. Many thermocouples can be connected in the same block. It is completely independent of types of thermocouple. But it has disadvantage is that computer takes additional time to calculate the reference junction temperature. So this is the disadvantage of software compensation. So we can go for hardware compensation. It can be viewed as inserting a battery and cancelling offset voltage produced by reference junction. Here, its speed is the main advantage, but it is suited to compensate only a particular type of thermocouple. As I say, in software compensation, there is it is independent of type of thermocouple, but here it is suited to compensate only a particular type of thermocouple. So this is disadvantage. Now, there are some things that we should note. Length of thermocouple probe. It should be immersed for a minimum distance equivalent to 4 times the outside diameter of the protection tube or well. The next one is location of thermocouple. Here, it should be located between the workload and the heat source and be located approximately one-third the distance from workload to the heat source. There are some thermocouple properties also. Now, the types of thermocouples based on metal combination B, R, and S. These are the types of thermocouples which are highly stable, but these B, R, and S, these types of thermocouples are low sensitive or they are least sensible. So next one is thermowell. What is the need of thermowell? So the main function of thermowell is that it provides protection to a sensor and sensing element from environment whose temperature is to be measured. Thermowells are mostly used in industries, or we can say it is used in industrial purposes. Here we can see the chart, and this table represents some common type of thermocouple. These are classified on the basis of materials which are used for these thermocouples. So,
Okay, thank you, Pallavi. Now I will continue with the simulation and the procedure part. So this is a COEP college simulator in which, you can see, it is a thermocouple diagram which is dipped in a particular liquid. It has both positive and negative ends. So first we have to select a thermocouple type. So let's just select a type J. So it shows what kind of material it is made up of, like iron and constant 10. Iron is positive and constant is negative. So we have to set a reference temperature according to which we have to calculate, we have to provide input values as well as to plot a graph. So let us just select it as 0. Then we have to press the get temperature button. It will show us a temperature value. Then we will see the input value according to this reference table. So in this, there are particular various types of thermocouple. We have selected J, so J type thermocouple, and these are all the values. So we have to input 169 degrees Celsius. So here you can see that this is temperature, and this is like minus 210, minus 211, minus 212, and so on. So we have to select 169. So this is 160, and its ninth element, that is 9.060. So we have to enter the value here, 9.060. Then we have to submit. I have done something error, so it is showing to recalculate. So let's just check me for this. Uh, so this is the input value. It shows correct. Now we have to get another temperature that is 206 degrees. So this is 200 and its sixth element that is 11.112. So we have to put here 11.112 and submit. So this is the second value. Then press again the get temperature button. It shows 114 degrees Celsius to 114 degrees Celsius, that is 6.032. All the input values are in millivolts. So now we can plot the graph. As you can see, it is a graph of output voltage versus temperature. And here you can see that it shows linear characteristics. This is the ideal condition. In real condition, it's not linear. Now it has another level. This is a static characteristics. Now we will move on to dynamic characteristics. So in dynamic characteristics, we have to find the time constant. This bare means the thermocouple without any insulation. So it has shown us the time constant of 8 seconds. Now we have to see a formula. This formula indicates that we for finding time constant, this is the formula. So here the I with two dots and comma represent as time constant. X is the thickness of the particular material. K is the thermal conductivity of the material. Then I with two dots is the density of material. S is the specific heat of the metal. L is the length of the element. For bare, so here it is given that for the bare element, the thickness is 1.25 mm and length is 100 millimeters. And this is the formula. Now, if we see here, so with sheet is just like a insulation, or in general terms, we can say that as every sword has its sheath. It is just like what we can say, myan. In Hindi, it's called myan. And these are the various type of materials. So, and here are the values. Just a second. These are here are the values of each material's density, specific heat. Let's just select SS304, and here are the various thickness. We can choose any thickness. Currently, I am choosing 0.5 mm. So now it shows the time constant as 9.55 seconds. Now we will add a thermowell. Thermowell is an external insulation, as Pallavi has already mentioned. So let's take another material, SS316, and its thickness, let it be 1.5 millimeters. And in this uh, particular thing, there are two filling materials, MgO powder and silicon compound. To find the time constant, we have to add each and every time constant of separate material. It's just like summation of all the time constant before this particular one. So let us just select silicon compound as the filling material. Now it shows us the time constant is 42.74 seconds. So this is the graph of it. This is a temperature versus time graph, and we can select a particular, like this is the bare one, bare without any insulation, bare thermocouple, then with sheet, and then with thermowell. So now we will go back to this. Here there are various videos and all. So here I end my virtual lab demonstration. So as ma'am have told, we have created a Google form. I would be very glad if you all solve it. I am putting it in chat box. Thank you. मॅम फॉर्मची लिंक टाकली आहे. तुम्ही पण सोडून बघाल तर चांगलं होईल. हॅलो.
हा, येस येस.
ओके मॅम, थँक्यू. Ma'am, can I stop presenting so that someone else
Yes,
can
yes,
start?
yes.
Thank you.
Ma'am, may I start next?
Yes, yes. You all solve the Google form questions which are shared by the Omkar.
Okay, ma'am. Hello, is my screen visible?
Yes.
Yes,
Okay, so hello, good afternoon. Today I am going to illustrate and explain the experiment on tensile test on mild steels. So basically starting from the very basic question. So what do we mean by tensile test? So tensile test, as we all know the definition of tensile strength. It is the strength or the capacity of a material that uh, capacity of material to withstand a massive amount of load. That is known as the tensile strength of that material. So the tests that we conduct to examine the tensile strength of that sample or material is known as the tensile test of that specific material. Or we can also put it like the fundamental test where we subject a sample, which is in this case the mild steel, to a very high amount of tension in controlled environment in our laboratories until the sample breaks down or fails to bear that tension, and is divided in pieces. So in this kind of test, we basically clamp the sample or the material, which is mild steel in this case, to a straining device or machine that exerts a lot or high amount of load on that material until it reaches the fracture point and gets destroyed. In this very specific experiment, we are using a universal testing machine, which looks something like this here. This is the universal testing machine or UTM. This mainly consists of the hydraulic cylinders which are present in here, and these are the two slabs in which we are going to place our testing or sample material. Uh, uh, there is also a load indicator connected. Besides of this is the load indicator with a large dial on it, and there are some pointers. There are also some dummy pointers on this load indicator, so that we can remember with the amount of loads that we have connected till now in the whole experiment. So now let us try and understand the whole stress strain relation a bit more closely and deeply. So this is the graph uh, of stress and strain relation of mild steel. This graph is basically divided in two major areas, which is the the elastic behavior and the plastic behavior. The elastic behavior is this small green portion at the very start of the graph, and the remaining whole portion is the plastic behavior. uh, in this behavior, in elastic behavior, there are there are two subparts in the elastic behavior. When this graph sorry excuse me. Yes, when the graph is in the region and the applied tension is removed in the elastic region, it can regain to its original shape. That's why it is called the elastic range or elastic area of the graph. uh, the major two types that are the major two types of the elastic behavior are when the applied stress uh, when on the application of stress, the material stretches proportional to the stress applied. That is, the stress and the elongation produced in the material are directly proportional to each other. That area of the elastic behavior is known as linear or proportional deformation. And once the material goes beyond this linear proportional limit, that uh, in that portion or area of the graph, even a small amount of stress can result in a very large amount of elongation or deformation of that sample material. This all process is conducted in this small green region, and after once the elastic behavior is or the elastic limit of that material is exceeded at this very point, it then moves on in the plastic behavior of area of the graph. In the plastic behavior, once the tension goes beyond this elastic deformation limit, uh, then there is no coming back for the shape of that specific material. Once the limit is crossed, the shape will remain as it is, and it will not come back to its original size and shape. There are, as you can see, there are three main regions in the plastic behavior, that is yielding, strain hardening, and necking. The yielding portion is also known as the flow region. In this region, a little bit increase in stress or tension on the sample can lead to a sudden loss of quality of that material or sample. Uh, and on the removal of, or as we all know, the removal of load cannot result in any good of that material. The damage has been done, so the shape can't be reformed. But once the limit is exceeded, this portion means the small amount of increase in force. Here, as we can see, the force is increased very minutely, but the length which we can see has increased tremendously. So this uh, means the damage to the material starts occurring once it exceeds the elastic deformation stage. After that, the second part in the plastic behavior is strain hardening or the material hardening. As we have seen in the previous region, the material has already undergone some serious quality damage, and the crystal lattice of the behavior of the material has already been disturbed. Uh, so, uh, so on further application of stress in the strain hardening region, the stress on the further application of stress, the stress on crystal lattice increases, and which leads to the hardening, which leads to a very distorted, distorted placement of those molecules inside the material, and which prevents the other molecules from shifting or moving in inside that material. But so it actually creates a barrier for some time to not let other particles move, but the always increasing stress or strain, always increasing stress of that load on the material keeps pulling and pulling the material, so that hardening or the trying to save that material cannot be hold on for a long time, and that that material distorts, or formation of voids or small holes in the material starts to take place. So in this material, in this stage, actually the material starts getting a bit stronger, but due to the ever increasing load, it eventually gets weaker, or the holes or voids uh, that are getting formed starts getting bigger and bigger. In this necking process, the third and last portion of the plastic behavior is the necking portion or the necking area. In the previous uh, area, we have seen that the material hardening process, in the material hardening process, the weakening starts, and due to the distorted or disturbed crystal lattice of the material, there is a formation of voids and cavities and holes, So these also add up to the reduction of cross sectional area. uh, Therefore, the constantly increasing stress and decreasing cross section results in loosening or weakening of the material, and hence it eventually reaches the fracture point. And once it reaches the fracture point, as we can see here, it breaks down or gets completely distorted, or can is divided in two separate pieces. So there are stages of ductile fracture in this sample material, that is mild steel. Uh, the mild steel is a ductile material, as we all know. It can be elongated and formed into wires and stuff. So the fracture in ductile materials like these are generally of cup and cone type fractures. That is, it takes place when when it is subjected to uniaxial force. That is, we always means in up and down motion we are pulling that sample material and we are trying to elongate it. So that kind of uniaxial application of force results in this kind of cup and cone fracture that we are going to observe in this simulation further. uh, so it starts from the main portion where we visibly can see the distortion or the destruction of material is in the necking process. The irregular crystal lattice, which had started in the yielding process, eventually grows, and in this process we see there are micro level of voids or holes getting formed, which eventually grows in the necking process, where we can visibly see that the shape of the sample material is getting distorted, and the micro level of voids are getting bigger in their size, or it is actually fracturing the material, and eventually when the fracture point is reached, it completely gets distorted. There is also a Indian standard. Sorry, yes, this is the relevant Indian standard, which is IS 1608, introduced in 2005. This is the Indian standard that is used to test the tensile strength of different materials in while testing the while making of these materials. Now, moving on to the simulation. This, as we all know, I've for previously mentioned, this is the universal testing machine, or UTM. Besides this is the load indicator. So first, this is the sample or the load which or the material that we are going to test today. This actually we consider only the portion from this to this region, and these two are the grips with which we are going to bound it in the UTM, or universal testing machine. First we will get the dimensions, the initial dimensions of the sample. So we are getting the diameter. We with the vernier caliper, uh, we'll get the diameter in both x and y axis, and then getting the average, we'll get the final diameter of the whole sample material. Then measuring the length. See, we have calculated this from only this to this point, as we are not considering this, as these are the grips. Later we puncture the sample material with uh, this hammer and the puncture tool. This puncturing is done at a distance of 2.5 times of the diameter that we have just calculated previously. After that, we take that sample. After we puncture the sample material, we plant the sample in the universal testing machine, or the UTM. Just a second. Yes. So this is how we plant or place the UTM, and this is the extensometer. We actually measure the extension initially. I forgot that point. In this, in the elastic behavior, as we can see, the force is increasing tremendously, but the increase in length is very in very small quantity, or we cannot measure it with the normal scales. So to measure the extension that we can get in the elastic behavior, we use this extensometer that can calculate very small or minute amount of change in the dimensions of that material. uh, Initially we have to set this at 0 or calibrate it. Then once yes also once we exceed this elastic behavior limit, we can then further calculate the length with normal scales, but till we'll cross the elastic limit, we have to calculate the length by extensometer. So now as we have placed everything in the UTM, we have placed our sample, we have also connected it with the extensometer. Now we start giving our loads. This is the whole data that we are getting. Here you can see the UTM is applying stress, and here we see the necking or the uh, narrowing of the diameter here, and eventually it breaks here. I would like to show you a video. This I hope you can see it. Is it visible?
Yes.
Yes. So this is the material, and these are the UTM plates. Uh, this here we can see the material is completely uniform, but here in this section we are seeing some distortion or disturbance in the structure of that material. This is known as the necking process, necking part of that sample due to excess load. And once the load exceeds, the material breaks in this way, which is not that efficiently shown in the simulation, but we have seen it now. So once the material breaks, we just stop the load indicator, and this is the data that we have got, we have achieved, we have got from the overall experiment that we have conducted. We can also download the data from here, and later this is the graph. This is the actual graph of this experiment that we have conducted, pretty similar looking to this graph, but this is the ideal graph, and this is the graph of the experiment that we have just now conducted. Next is this graph. This is the load and extensometer reading. uh, Extensometer, we just saw that the equipment that we use to measure minute change in dimensions. Here we can also get the uh, slope of this load extensometer graph. We'll be needing this slope for the calculation of uh, modulus of elasticity. Next, here we take the broken sample, and then we calculate the, here we, here in this we, the narrowed portion of the sample, or the net elongation or the reduction in the cross sectional area or the diameter, we have to calculate that also. So we are just calculating that here. So that we for previously we calculated the final diameter. This is the final length between two punctures, that is 29.62 mm. And here we just put our calculated observations and calculations, and we are done. I have previously calculated a result. So in this way it will show you the result. These are the actual values that we are supposed to put, uh, that are the actual values, and these are the entered values. And it will also show you the percentage error that you have committed while calculations or doing the experiment. So thank you. I'll just Hello.
Okay, very good, Vinmay, Pallavi,
Thank
and Omkar. Anyone else want to present?
Yes, ma'am. आकृती आहे.
आकृती. तू कुठला व्हर्च्युअल लॅब दाखवणार आहे?
एक्सपेरिमेंटचा नाव आहे रेझिस्टिव्हिटी ऑफ सेमीकंडक्टर बाय 4 प्रोब मेथड.
ओके.
शॅल आय प्रेझेंट?
Yes. Vinmay, which virtual lab you used?
Um, Ma'am, these MHRD virtual labs, Government of India.
Okay, it's very good.
Thank you, ma'am.
Yes, Akruti.
येस मॅम. इज द स्क्रीन विजिबल?
Yes.
So good afternoon to everyone. So today we are looking forward to the experiment named as resistivity by 4 probe method. So aim of this experiment is to determine the resistivity of semiconductors by 4 probe method, and along with this we will observe the graph of resistivity against the temperature. So quickly revising few theory parts of the few theory parts of about the resistivity. So we know that the resistivity is defined as the resistance offered by a conductor having unit length and unit area of cross section. And here we can see that the formula of resistance is given as R is equal to rho L by A, where R is resistance, rho is resistivity of conductor whose unit is ohm meter, L is the length, and A is the area of cross section. So in semiconductors, the forbidden gap between conduction band and the valence band is small. At 0 Kelvin, valence band is completely filled and the conduction band may be empty. When some amount of energy is passed or applied, the electrons easily move to the conduction band. In the normal conditions, semiconductors are poor conductors, but when the temperature is increased, the density of charge carrier increases, and the density of charge carriers increases and the resistivity decreases. So the few things which we are looking for, we have to take care of are the diameter of contact between metallic probes and the conductor should be small as compared to the distance between probes. And now here in this figure, in this second figure, we can observe, we can see that it is the uh, it is a slice or a part of a sample. The sample has its thickness as W, and these are the 4 probes arranged in a linear straight line or in a straight manner with having equal distance of s centimeter between them. And this is the circuit diagram which we are connecting. Here we can see that the first and fourth probes are used to supply the current, whereas the potential difference is measured across second and third probe. Now when we are looking for to the resistivity of a slice of semiconductor, the formula is as rho is equal to rho naught by function of W by S. And when it is its thickness, the metal tip is very small and the sample thickness is greater than the distance between probes, the formula is given as rho naught is equal to V by I into 2 pi s, where V is the potential difference between inner probes and I is the current through the outer pair of probes in amperes, and S is the spacing between the probes. Temperature dependence of resistivity of semiconductor, we know that the total electrical conductivity can be calculated as the sum of conductivities of valence band and conduction band. Resistivity is the reciprocal of conductivity, and its temperature dependence can be calculated through the formula rho is equal to a exponential of Eg by 2 kT, where Eg is the band gap of material, T is the temperature, K is Boltzmann constant, and now these are a few applications of this are first is remote sensing areas, second is resistance thermometers, third is induction hardening process, fourth is accurate geometry factor estimation, and fifth is characterization of fuel cells bipolar plates. So we will now see the stimulation of the experiment. Now to the apparatus used here are this is the current source, this is the voltage source, no, this is the machine, this is the digital microvoltmeter to measure the voltage. This black portion is called the oven. This metallic part is the whole assembly of probes. Like as we see the cross section, we can observe that there is the sample placed, and these are the four probes named as probe 1, probe 2, probe 3, and 4. This is the controlled oven, which is used to heat the sample, and here we can observe the increasing temperature. Few parameters are available here to set, such as we can select the material. Here we have two options of germanium and silicon, as they are more often used semiconductors. So we are taking a germanium. We can select the range of current. We are taking it to be 20 milliampere, and selecting the current to be 8 milliampere. So throughout the experiment, we have to keep this current constant. These are the four. Uh, this is the range of oven, where we can select its range as into 1 or into 10. These four buttons are used to handle the oven. First is set, so we can set the range of the temperature, uh, maximum temperature. So we are taking it to be about 75 degrees Celsius, and then clicking on the run. When we will click on the run button, we will observe that the temperature starts to increase. Wait button is used when we have to take the readings, such as in this we will be taking readings at an interval of 10 degrees Celsius, so that we have a uniform readings. And measure is used to measure the overall readings. And here the range voltmeter gives us the options to measure voltage accordingly. Options are 1 millivolt, 10 millivolt, 100 millivolt, 1 volt, and 10 volt. We are keeping it to be 10 volt. Uh, we are now clicking on the run button, and as soon as we click on the run button, we can observe that the temperature here starts increasing. Now we will stop this. We will wait this at the 35 degrees Celsius, and it is now this is at 35 degrees Celsius. We have clicked on the wait button. Now we will observe that at the temperature 35 degrees Celsius, the voltage comes out to be 0.2205 millivolt volts. So now the observation is table is given below, but we will write it in a rough, so that at the end we will put all the values at a time. Now we will click on the run button again to take another reading at the point where the temperature is 45 degrees Celsius. So when the temperature is at 45, we will click on the wait button again. uh, So here is the another reading. When the temperature is 45 degrees Celsius, the voltage is 0.2085 volts. Again continuing the same process, we will be waiting. We will be observing the temperature, observing the voltage when the value of temperature is 55 degrees Celsius. Uh, so this is 55 degrees Celsius. At this point, the voltage is measured at 0.1979. Clicking on the run button again, we will now observe the temperature at 65 degrees Celsius. Um, when it is 65 degrees Celsius, the voltage is measured to be 0.1883. Now clicking on the run button again, and it will automatically stop when it reaches the maximum temperature of 75 degrees Celsius. So while it reaches the 75 degrees Celsius temperature, I will be uploading the data which I have calculated here. So here we can observe that the temperature is given in kelvins, and we have calculated the temperature in degrees Celsius. So we will be converting the temperature in degrees Celsius to the Kelvin. So here the first temperature was 35 degrees Celsius, which comes out to be 95 Kelvin, and the voltage was 0.2193, and the constant current was 8 milliampere. The mathematical input is given already, so the resistivity comes out to be 0.2258. Another thing which we have to keep in mind is that in this case we have considered the distance between probes to be zero point 0.2 centimeter and the thickness to be 0.05. So from the standard table, the value of FWS comes out to be 5.98. The next temperature taken was 45 degrees Celsius, which is 113 113 Kelvin, and the voltage is 0.2085. And it's the third observation where the voltage is 50, where the temperature is 55 degrees Celsius. It is 131 Kelvin. Voltage comes out to be 0.1979. Constant current is 8 milliampere. We are now taking it the temperature to be 65 degrees Celsius, which is 149 Kelvin, and the voltage is 0.1883. Constant current to be 8 milliampere, and the last observation is 75 degrees Celsius, which is 165 Kelvin. The voltage measured is 0.1798, and the constant current is 8 milliampere. Now we can observe that the all the we have got all the observations for the resistivity in this table, and by clicking on the this we can observe the graph. In this we can observe that as the resistivity as the temperature increases, the resistivity of semiconductor decreases. So concluding the experiment, we have observed that when we increase the temperature, the resistivity decreases. And as we have taken here the example of pure germanium, so resistivity of pure germanium under standard conditions comes out to be 60 ohm centimeter. Thank you.
ओके, व्हेरी गुड. आकृती, विन्मय, ओमकार आणि पल्लवी चौघांनी पण खूप छान प्रेझेंट केलेलं आहे. ऋतिक, तू काय करणार होता?
मॅम मी आता क्विज सेंड करू का? म्हणजे
आत्ता नको, आपण नेक्स्ट सेशनला घेऊया. मीनवाईल बाकीच्या मुलांना निरोप सांगायचा आहे की जे लोक प्रेझेंट करतायत तेच फक्त प्रेझेंट राहिलेले आहेत. बाकीच्यांचं काय आहे, त्यांना प्रेझेंट नव्हतं करायचं तर ते आलेलेच नाहीयेत, तर असं चालणार नाहीये. तुम्ही जरी प्रेझेंट नसाल करत तरी बाकीचे काय प्रेझेंट करतायत हे ऐकण्यासाठी आणि त्यांनी जो क्विज तयार केलेला आहे त्याला रिस्पॉन्स देण्यासाठी तुम्ही सगळ्यांनी प्रेझेंट पाहिजे ॲक्टिव्हिटीसाठी. हा निरोप बाकीच्या सगळ्यांना सांगायचा आहे. आणि जे कोण चांगला रिस्पॉन्स देतील तुमच्या क्विजला किंवा ज्यांना आउट ऑफ मार्क्स मिळतील तुम्ही सांगितलेल्या क्विजमध्ये, तर त्यांना त्या ॲक्टिव्हिटीसाठी +5 मार्क्स देण्यात येतील. हे तुम्ही बाकीच्या तुमच्या मेंबर्सना पण सांगायचं आहे. आता तुम्ही हे आत्ता इथे लाईव्ह प्रेझेंट केलं ना एक्सपेरिमेंट्स. आत्ता तुम्ही सगळ्यांनी लाईव्ह प्रेझेंट केलं ना
हो मॅम.
हे.
येस मॅम.
हो मॅम.
मग तुम्ही आता क्लासरूमवरती काय अपलोड करणार आहात?
मॅम त्याचं रिझल्टचा स्क्रीनशॉट टाकू शकतो.